Welcome everyone. This is DW301 Basic Electronics, and now we shall discuss about semiconductor physics. In the previous lectures we have already discussed about the historical development of the electronics and some of the industrial and some of the common examples of the electronics. So now let us start with the semiconductor physics. The first question arises, why we are interested in semiconductor physics, and I guess you people can answer now. As we know, the electronic devices or the electronic equipments or instruments are made of semiconductor materials, and we know that in our day-to-day life, in our day-to-day life, in manufacturing industry, in space, in communications, in defense, medical, in various fields, we are using electronics extensively. So in order to understand the working of electronic devices, we need to understand the physics behind these materials by which these electronic devices are made. So first we need to understand the physics of the materials by which these electronic devices are made. Okay, I think this is the motivation behind the interest in semiconductor physics. Okay, let's start. First, we will start with the conduction of current. As in the first lecture, when we were defining the various terms, we defined the electronics, and the definition was like this. The electronics deals with the conduction of electrons in semiconductors. So let us discuss about the conduction of electrons in various kinds of materials. So let's start, and here I am using the handmade slides, and whenever it is required to write something, we will do accordingly. So for conduction of current we need charge carriers. So for the current conduction, the charge carriers are needed. As we are familiar with a very popular relationship and very basic, Q is the charge, and IT, delta Q, is equal to delta Q equal to I into delta T. So this is the uh, very popular relationship between charge and current, and the more advanced form is the dq equal to I dt. So you must be familiar with these differential forms of the equations. Okay, so now let us discuss the conduction of current in various kinds of materials. So in gases, the positive ions and electrons at some particular temperature, pressure, what really happens, there is a ionization at some particular voltage. When we apply some voltage between some anode and cathode, and there is ionization of gases takes place, positive ions, positive ions and electrons are the reason behind are responsible for the conduction of current in the gases. And in liquids, we know, in liquids, and if we talk about electrolytes, the molecules break up into two parts, in positive ions and in negative ions. Here I have used the abbreviations for the positive and negative, and or you can say the symbols. And here one example is given in any electrolyte solution. The here if the NaCl solution is there, Na plus ions plus chlorine minus ions, and sodium chloride breaks into the sodium ion and chlorine ions, and under the action of electric field, which happens when we put two electrodes, anode and cathode, and the negative charge is attracted to the positive electrode. What is positive electrode? Anode is the positive electrode, and the positive charge is attracted to the negative electrode, and negative electrode is the cathode. And this kind of phenomena we have seen in the electrolytes and in the batteries. In the batteries, the H2SO4 is the electrolyte, and H2SO4 breaks into the H plus ions, SO4 minus double minus ions. So this happens in the liquids whenever we conduct the electricity in liquids. So basically we are just briefly discussing these terms as we are interested in the semiconductors. Okay, now we will move to the next slide. Next is this. Actually these pictures are randomly placed. So next is this, second is this. So solids. So in solids, depending on the kind of solid, there can be various types of charge carriers. So in solids, the theory is different. Depending on the depending on the kind of solids, there can be various types of charge carrier. There could be some holes or electrons, and as we will discuss in subsequent sessions. Okay, so first we need to understand that on the basis of conductivity. What is conductivity? Actually, it tells us how well a material will allow electricity to travel through it. So conductivity is the property of any material which tells us how easily the material will allow to flow the electrons in the influence of electric field. So here as we are studying the electrical or electronic engineering subject, so you should assume whenever I am talking about conductivity, then this is the electrical conductivity. We are not talking about thermal conductivity. Okay, so this is not a mechanical class, it is an electrical class. So you should assume this, that whenever I am talking about whenever I am saying the word conductivity, this means electrical conductivity. Okay, so solids are classified into the three types in according to the conductivity. So insulators, semiconductors and conductors. So first let us briefly discuss the insulators. And the insulators, and they don't have any kind of charge carriers, and the example is the dielectric material, the sigma insulator. Sigma is the symbol for the conductivity here. Sigma insulator tends to 0. So these are the dielectric material. All dielectric materials are supposed to be perfect insulators, but actually they are not, and this is the different theory. And all you need to understand, all those materials like mica, paper, plastic, wood, all these are insulators. So and the conductivity of the insulators, whenever we apply the electric fields, electric field in the insulator, there is no effect of the electric field, there is no conduction of charge. As we know, if we need to connect a circuit, we cannot use a rope, we need to use a wire. Okay, so why we cannot use a rope? Because that does not allow to pass the that does not allow to conduct the electrons under the influence of electric field. Okay, now the next extreme thing is the conductors. So in conductors there are large number of charge carriers, very large number of charge carriers, and the examples of the conductors are metals. All the metals are good conductors of electricity, and even they are also good conductors of heat. And we are not discussing heat here, we are only discussing the electricity. So metals like silver, aluminum, copper, all are the very good conductors. And we can say the conductivity of the conductor tends to infinity, is very high, very high. So the conductivity of the conductors is very high. And there are third type of materials which are in between, which are in between, in between insulators and conductors. These materials are having the conductivity in between in between insulators and conductors. So, and the examples of these materials are silicon, germanium, carbon, etc. And we will definitely discuss these materials in details in the subsequent sessions. So now you are familiar with the types of solids. Okay, now we shall move to the next slide. And what is the next slide here? I think conduction. Yes, this is the next slide. Okay, the conduction now, before going to the discussion of or you can say before moving to the discussion of semiconductors, first we shall discuss very briefly the conduction of current in conductors, and there will be some concepts that we will use in the semiconductors. Okay, so first we will discuss the conduction of current in conductors. We need not to discuss anything about the insulators, as they are not good conductors of electricity. So we will discuss the conduction in conductors or metals. So in any solid atoms, in any solid, atoms are closely packed. First we need to understand little bit about the structure of metals or the solids. In any solid, atoms are very closely packed, and there is a regular arrangement of atoms in solids, which is called crystal structure. And whenever there is a periodic structure, arrangement, then that is called the lattice structure. So I hope you all are familiar with these with these basic chemistry terms. And if you are not, then what you need to do, all you need to understand, all you need to do to learn some basics of the chemistry from the, I think of you all are familiar with these terms, because these all are these all basics of the chemistry are taught in the 9th and 10th class. So the solids which are called crystal structure or lattice structure. Okay, and one more thing I would like to mention here: whatever basics is necessary, I will discuss that. So this is the point. So you should not bother about the basics of the chemistries. Here I am discussing you, and if you want to know about more about these crystal and lattice structure, then definitely you should refer some basic chemistry book. But whatever information I am providing here is sufficient for the learning of semiconductors. Okay, so okay, let's begin. So in conductors or in any solids, atoms are closely packed, and there is a regular arrangement of atoms in solid, which is called crystal structure and lattice structure. It's a periodic, whenever the arrangement is periodic, then this is called lattice structure, and whenever there is a regular arrangement, then this is called the crystal structure. Okay, in metals, outermost electrons are very loosely bound. So in metals, the outermost electrons are very loosely bound. As we know, the outermost electrons are very far from the nucleus. You can understand it by this. Here, wait. Okay, so in metals, the outermost electrons are very loosely bound. So as we know the basic structure, if there is a nucleus and there are orbits or more orbits, here we are talking about the outermost orbit, the electron in outermost, this. So we are talking about this electron here. So here the electrons are loosely bound. As we know, the electrostatic force will be less. Here the nucleus having the positive charge and electrons having the negative charge, but the binding force is decreasing, because we know the electrostatics force, which is the Coulomb force, is the KQ1 Q2 over R square. So it is inversely proportional to the square of the distance. As the distance is increasing, the electrostatics force, the electrostatic force which is acting between these two is decreasing. So the electrons are very loosely in the outermost orbits. Electrons are very loosely bound. Okay, now we shall come to our slide back. So in metals, outermost electrons are very loosely bound, and a very small amount of energy is sufficient to dislodge them from the atom. So if a very small amount of energy from some external electric field, from some elevated temperature, whenever we increase the temperature of the surrounding, and as we know, the whenever the temperature of the surrounding increases, the materials get heated, and heat energy is supplied. Okay, heat energy is supplied, and some kind of flashlight, or you can say some if we provide some very small amount of energy by any mean, by some by some light source, by some electric field, or by some elevated temperature. So the very small amount of energy is sufficient to dislodge them from the atom. Okay, now we will move to the next slide. This is the next slide. So here you can see the two-dimensional representation of metallic crystal. So this is a two-dimensional representation, and this is just a cross section, and you can assume the layers above and below. So at absolute zero, these can move so freely. At absolute zero, these electrons can move so freely, conductivity so freely, so the conductivity tends to infinity. Resistance to oppose to charge carrier is zero. So what you need to understand, that at t equal to 0, at t here we will use some of the basics from the kinetic theory of the solids, kinetic molecular theory of the solids. So first you need to understand that this is the regular arrangement. This is the regular arrangement of the solids, and here you can see the positive ions. Whenever an electron is dislodged from some atom, then atoms become a positive ion, and a free electron is available. Okay, so now we are discussing some of the terms related to the kinetic molecular theory of the solids. At absolute zero, these electrons can move so freely. So the here you can write. So the conductivities here, this must be so here. So the okay, I will correct it, and I will send you. Whenever I will send you, I will correct this mistake. Okay, so the conductivity tends to infinity, and the resistance to oppose to charge carrier is 0. So at t equal to 0, kinetic energy is 0. As we know by the basics of the kinetic theory of the gases, here you can understand the the energy at any temperature is like 3 by 2 kT, is proportional to the kT, some constant multiplied by kT. And we know there is a formula for velocity also, which is some under root kT. So here what you need to understand, only we are not interested in those formulas, but as we know, the energy of the atom or energy of the electron at any particular temperature in any solid is given by 3 by 2 kT. This is from the kinetic theory of the solids. Okay, so all you need not to learn these formulas. Okay, all you need to understand the proportionality here, E and T here. If T is 0, then energy will be 0, and any kind of energy will be 0 and as we can see, V velocity is 0, and at under root kt some constant multiplied by under root kt. So there is a different constant here. So but the bottom line is this: if T is 0, then velocity is 0. The material will not vibrate or move. So if there is any external field, then these free electrons can move so freely, because at t equal to 0, what really happens, these atoms which are vibrating, actually these atoms are also vibrating. These electrons are free to move. Electrons are moving with some thermal velocity v, and which depends upon the temperature. But when the T is 0, then there is no thermal velocity, electron is available, and whenever a field is applied, electron get influenced by the field, and there is a force on electron. Which is F equal to QE, where is the Q is the electron here, then F equal to E into E. Whenever an electric field is applied, there is a force on electron, and whenever there is a force, there will be some acceleration, and electron will start moving. And whenever the electron moves, we are talking about here one electron, and this happens to all electrons. And whenever there is a charge which passes through some cross section area, there will be some current. Okay, so this is how the current conduction takes place. And we have discussed the one condition: when t equal to 0, the resistance of the conductor becomes very less, or you can say ideally 0. So but at some elevated temperature, kinetic energy is imparted in positive ions, and the kinetic energy shows itself as a vibrational energy. So here first when we started, we were discussing about the crystal structure, and we started from the temperature T equal to 0 for the excuse me, for the metals. We are discussing here for metals only. So what really happens for the metals at T equal to 0? At T equal to 0, kinetic energy is 0, and the resistance offered by the metal, because as we know, there is a formula for resistance: R equal to rho L upon A. Rho is the resistivity of the material, length of the material, A is the cross section of the material. We all are familiar with this very famous formula, R equal to rho L upon A. So every metal will have some resistance, and that will depend upon the resistivity, this term. Okay, now now what is the next point? At some elevated temperature, kinetic energy is imparted in positive ions, and whenever the temperature, because as we have assumed T equal to 0, and what is T equal, what do we mean by T equal to 0? What is the temperature? T equal to 0. T is the absolute temperature. T equal to 0 means T is equal to 273 plus T in degree Celsius. This is the normal temperature T, which is our ambient temperature actually. So when we are talking about T equal to 0, then this T equal to this T equal to 0, then T 273 plus T, this T will be minus 273 degree Celsius. So this is a special case actually. When we are saying that T equal to 0, then kinetic energy is 0, then this is a special case, and in that condition the resistance of the conductor is almost zero, and the conductivity tends to infinity. So as we know that there is an inverse relationship between conductivity and resistivity. Conductivity and resistivity 1 upon rho. So if conductivity tends to infinity, resistivity tends to 0. So this is very simple, you can understand. So now the next point is this: at some elevated temperature, and because as we know, all the materials and all the conductors by which we are dealing are at the ambient temperature, and ambient temperature is the temperature at which we are working. 27 degrees Celsius, 25 to 40 degrees Celsius, between in summers between 25 to 40 degrees Celsius, 40 in even in Agra 45, and in winters minus 10 to sorry 10 to 15 degrees Celsius. Okay, so there is a pause. Okay, welcome back. At some elevated temperature, kinetic energy is imparted. So, whenever we increase the temperature from T equal to 0 to some elevated temperature, and for the ambient temperature, T will be approximately 300 K Kelvin. So 273 plus 27, if we take an average temperature of 27-28, then this will be 300 K. So definitely, as we know, the energy is 3 by 2 kT, and K is the Boltzmann constant, and temperature and the T is the absolute temperature. Then definitely there will be some energy imparted, and this kinetic energy shows itself as a vibrational energy. Here you can see some vibrations here. So this is the crystal structure of solids. All the atoms are vibrating, and the vibrations are very random. Vibrations are very random in nature, and they are vibrating at the mean position. So all you need to understand this from the kinetic theory of solids. Okay, next point is this. Now we shall move to the next slide. Okay, now next slide is this. So electrons collide with vibrating ions. Electron collide, definitely electrons will collide to the vibrating, and because electrons have also the energy, and E equal to 3 by 2 kT, they have some thermal velocity, and these atoms are also vibrating, then definitely there will be some collisions, and these collisions could be elastic and inelastic, and here we will talk about inelastic collisions. And these vibrations of positive ions are random, as this we have already discussed. So first here we in order to understand the conduction of solids, first we will discuss the absence of electric field. What happens when there is no field applied on the conductor? When we do not apply any kind of field on a conductor, then what really happens? So here you can see, if we do not apply any kind of field, then an electron will move randomly. An electron will move randomly. Here you can see an electron will start from here, it will move, then it will again, and it will collide with some atom, then again it will move, and the direction will change, and this will be the behavior. So if we observe an electron with the help of microscope, then what really happens? And you can see there is a definite probability that it will come back to its original position. It will come back because the motion is very random. So here we are talking in terms of probability, because we cannot see these things with the naked eyes, so we will talk about probability. Okay, so here is a mean free path. So distance between two collisions. So there is a mean free path which is called the distance between two collisions, and distance between two collisions is not constant, but we can define this mean free path. So because these distances are different, you can see this is different, this is different, this is different, this is different. So we define a mean free path. So this zigzag motion is random, so there is no net motion in any direction. So this, the last point is the bottom line. So whenever there is no field, electrons are moving, but they are moving randomly, and the probability of returning back to the original position from where the electron had started is very high. So here we are discussing absence of electric field. So in next slide we will discuss in the presence of electric field. Okay, this is the presence of electric field. So when we apply an electric field, here you can see the direction of electric field. This is the direction of electric field, and if this is the direction, this will be positive and this will be negative. This is how the electric field is set up. And now what happens, whenever a force in the opposite direction of electric field will work on whenever a field is applied, a force in the opposite direction of electric field will work on electron. Whenever we apply the electric field, then the force is F equal to QE. This we have already discussed. Q is the charge of the electron, and this is negative, and that's why F equal to minus E into E. So the minus small e into E, that's why the direction is opposite. Here this negative sign signifies the direction of force, because force is a vector quantity, as we know that. A small velocity is contributed by electric field. So a small velocity is contributed by electric field, and definitely when the force will act on the electron, then the electron will move in influence of that force also. It was moving, the electron was initially moving actually like this, but now there is a force acting on the right side. So now what happens, the electron will not come back to its original position. Now this will be clear. Here you can see the displacement, a net displacement of electron. Here there will be some kind of net displacement from the original position, and you can see here electric field imparts certain velocity called the drift velocity. Because in the influence of electric field, electron drifts away. So the electric field imparts actually the thermal velocity is there. Thermal velocity is like this. Electron will be like a system on which various forces are working. The thermal velocity, in the influence of thermal velocity, it is moving, but electric field is also working. So it will also try to follow the electric field. So there will be some vector sum of forces, and all things will happen there, and finally there will be some net displacement, and this is how current conducts inside the conductors. So here the next point is drift velocity. So U, in some books you can find U, and here for our purposes we will use VD. We will not use this U, we will use VD. VD is the drift velocity is proportional to the electric field. As we know, this velocity is imparted by the electric field, and there is a constant VD equal to minus mu E. So this mu is very important. This mu is called the mobility of the electron. This mu is called the mobility of the electron. Okay, now we shall move to the next slide. Here this will be more clear. I have made a picture in contrast. This here you can see both pictures in a same frame. when there was no electric field, the electron was moving like this, and when there was electric field, so there was some drift. So this is how the conduction of current takes place inside the conductors. After n number of inelastic collisions, electrons shift towards the opposite direction of electric field. So this is the direction of electric field, and electron is shift towards the opposite direction of electric field. So Vd equal to minus mu E. So let's define the mobility now. So mu is the mobility of electron. Mu is the drift velocity of a charge carrier under the influence of unit electric field. So if for defining the mobility, all we need to do, we need to provide a unit electric field. What is the unit of electric field? A unit electric field means 1 unit of electric field. So here the unit of electric field is volts per meter. If we provide an electric field of 1 volts per meter, and then the drift velocity of a charge under that field, drift velocity of charge carrier under the influence of that unit electric field will be the mobility of that charge carrier. And here in particular we are talking about electrons. This is the mobility of electron, Vd equal to minus mu E. So now there is a homework for you. You need to calculate the unit. Now calculate the unit of mobility. What will be the unit of mobility? So this is a homework for you. Unit of mobility. Find out. Now you know the unit of electric field, and the unit of velocity is known. Use the same system, CGS or MKS, and then you can find the unit of mobility.